Number system is called the decimal system, which means it's base 10. If you didn't know, this is also called the Hindu-Arabic numeral system. But we've been using this for a long time, as it's a very powerful and useful system. The reason why it's base 10 is most likely because we have 10 fingers on our hands, right? You count 1 through 10 on your hands, then you have to quote unquote roll over to a new place to be able to keep counting above 10. And so this place value system that the Hindu-Arabic numeral system designed is powerful because you can keep counting on up to, millions, billions, trillions. There are other base systems than the decimal one. I'll just write decimal base system. This is, of course, we go 0, 1, 2, 3, 4, 5, 50, 6, 7, 8, 9. And then when we round up to the next one, when we add 1 to 9, we move a place, we put the 9 place to 0, and then we put a new place in it, which goes right here. The more to the left you place, the bigger and bigger the number becomes. The more to the right, it becomes smaller. Now we can count above the number 10 by using this second place value. And you can keep adding place values to it because you can just keep writing numbers left and right. Another number system is binary. This is used mostly in computing. And these only have two digits, 0 and 1. When you add 1 onto 1, now we get a new place value. This is where the 1 was, and then we add a 1 to the new place value. So like in decimal numbers, we can have 36,784.96. In binary, we can have 10110,101, something like that, and you can convert between the two of them. Now, there's another system that's used in computing called hexadecimal. This is where there's 16 unit digits that we use, and we can use place value and everything with that just fine. But what's interesting is, where do we go after we get to 9? Because you can't just write 10, that uses 2 place values. You have to use a different symbol for it. So how do you go up above 9? Well, we just actually use the alphabet. A, B, C, D, E, and F. So we have, you always have to have 0 in these. That's how you designate a place value that has nothing in it. But the actual counting begins at 1. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 digits plus 0 makes 16 digits. And so how do you go on to the next space? Well, you do a 1, 0. And we keep counting. We keep counting on up. So it'd be, let me write it down here: 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then you go like 1A, 1B, 1C, 1D, 1E, 1F. So 1F should be a single 16th place value plus the F, which is the 15th place value. So this should be 31. And then when we add 1 onto that, it becomes 32. But that becomes a new place value, so we get 2, 0. And so on and so forth. So you get these numbers that have, you can have like 3A, 5, D, 2, 4, 7, CE. Numbers like that. This, of course, would be a very large number because it's hexadecimal, meaning it has each place value is 16 times as big, whereas our decimal system, each place value is 10 times as big. So hexadecimal gets very, very large. This would be a huge number in the decimal system. Now there are like pseudo bases that are also used. Time is kind of a pseudo base system. That would be base 60, because we count up to 60 seconds and then we move back down to 0. So we have 58 seconds, 59 seconds, and then we have 0 seconds, but we have 1 minute. So we've rolled over the seconds into a minute, and we keep going. When we get 60 minutes, we have 59 minutes, 58 seconds, 59 minutes, 59 seconds. When we have 0 seconds, we rolled over, and that became 60 minutes, but that also rolls over, and now we have 1 hour. Of course, at this point, that's when the system breaks down, because there's only 24 hours in the day when it rolls over, so it's no longer base 60, but it's kind of a pseudo base 60, if that makes sense. So why are we talking about base systems and these place values? Because place value is very important to how we write numbers. In fact, every place, every position in a number, this is our decimal system here, every single one of these place values has a very specific meaning, and it's important when you do arithmetic on decimal numbers. I'm not really going to worry about talking about binary, hexadecimal, or any other base systems. We're really going to be working with the number system that we use. So let's look at this number here, 13,406. Now this is, in the decimal system, we can rewrite this as 1 times 10,000 plus 3 times 1,000 plus 4 times 100 plus 0 times 10 plus 6 times 1. Each one of these places, the 6, the 0, the 4, the 3, and the 1, has a designated power of 10, as it's called. 10,000, this is going to be 10 to the 4th power. 1,000 is 10 to the 3rd power. 100 is 10 squared. 10 is 10 to the 1. And then 1 is 10 to the 0. So they're all powers of 10. That's why we call it a base 10 system. They're all powers of 10. Now, what you don't ever see in numbers like this one is the decimal point. If you're not seeing the decimal point, that's because it's assumed to be on the very end of the number, the very right of the number. The decimal point, however, is the anchoring point. It's necessary to understand the rest of the place values. But because a lot of times we work with numbers that are not a decimal number, we just kind of drop it to assume that it's there, but it's always there. So let's look at this decimal point at this number here, 1,534.817. All right, we have place values here, right? We have the 4, the 3, the 5, and the 1, just like we did in the previous problem. It's going to be the first place value, the second, the third, and the fourth. What happens when we move to the right of the decimal point? Well, let's just kind of look at these numbers here, using the same idea that we did with the 13,406. We have 1 times 1,000. Now you write it like this. 1,000 is the same thing as 10 cubed. In other words, 10 times 10 times 10. That's what 10 cubed is. Plus 5 times 10 squared. 10 times 10. That's what 10 squared is, which is 100. Plus 3 times 10 to the 1, or just 10. There's only one factor of 10 in there. And then plus 4 times 10 to the 0. Anything to the 0 power is 1. So we have really 4 times 1, which is 4. Now, what's 8 going to be multiplied by? Well, let's look at the powers here. 3, 2, 1, 0. Following the same pattern, it's going to be 10 to the negative 1. And the negative 1, what that does is it makes it 1 over 10. That's what the negative power does, is it flips it. And 1 over 10, that's the same thing as 0.1. So 8 times 0.1 is 0.8, which is, in fact, this place value right there, 0.8. Then we can continue. 1 times 10 to the negative 2, which is going to be 1 over 100, which equals 0.01. So again, we have the this place value there, the 0.01 place. And finally, we have 7 times 10 to the negative 3. So we still have powers of 10. What you'll notice, though, is that as we go right, we get smaller. Smaller and smaller and smaller. It gets closer and closer to 0. And as, of course, we go left, it gets bigger. We do have names, just like this. Let me do this here. This is called the ones place. This is the tens place, the hundreds, the thousands place. Going backwards, we don't have ones. The ones is kind of the staple. That's where the decimal point, the decimal point's kind of put like right here. And so the ones is kind of the staple point. But the next point here, this is the tenths. Tenths with a TH. This is the hundredths. Hundredths. And then this is the thousandths. I gotta make sure you can spell right. Thousandths. And so on and so forth. So just like here, we have the tens, hundreds, thousands. We go backwards with the tenths, the hundredths, and the thousandths with a TH on there. Here are 3 numbers that are written in English. We're going to translate them to the decimal number system that we use. What's important to note here is the AND word always means the decimal point. So wherever the AND occurs, the decimal point will happen there. So the first part is going to be probably the easiest part to do. That's going to be the whole number part. So 54 is 54 and then the next part here, 2/10, that's going to be the decimal part. What you're looking to do is make sure the last place of the number that's written there, be it 2/10, the next one is 86 hundredths, the last one is 367 thousandths. The tenths, hundredths, thousandths, that's where it tells you where the number ends. Okay? There should be nothing written past that point. So understanding the place value of this number here is going to help you. So we have, right, I could write like we have 3, 4, 5, 6, 7, 8, and put the decimal point there. Right, we have the hundredths, H. This is the, all right, hundreds be with an S, and then the 4 is the tens with an S. This one's going to be the ones with an S. This is the and this place here is going to be the tenths with a TH. This place here is going to be the hundredths with a TH. This is going to be the thousandths. I didn't think about the TH. 2 T's. I'll do thousandth with a TH. And then, of course, you have the next one is going to be the 10,000ths, and the 100,000th, and the millionths, and so on and so forth. So understanding the place value is going to be helpful when you have these types of problems. So 2/10, well, the tenths position is right there. Let me do it in red here. The tenths are going to be right there. So we know we need to end the number the first spot after the decimal point. And that's simple because it gives us 2/10. So all we have to do is write 2 there. And that 2 is in the 10th spot. So that would be 2/10. So 54.2 is 54 and 2/10. Okay, so let's use that same idea on the next one. 13, that's easy. 13 and 86 hundredths. Hundredths, right there. So we need to have two numbers past the decimal. Well, that's fine because it gives us two numbers, 86. And if we write 86, this spot here is the hundredth spot. So that would be 86 hundredths. It ends in the hundredth spot. That is correct. Last one, 1 and 367 thousandths. So thousandths right here. We know we need to have 3 place values because there's three values past the decimal. And we have 367. That is 3 numbers, so 367. And that ends in the third spot. The third spot is the thousandth spot. So that's the correct answer there. Now, real quick, what if we had something like 7 hundredths? That's all we had is 7 hundredths. Now, what you don't see is the and number. That's because there is no whole part here. I haven't said 54 and 13 and 1 and, which means that there's a 0 in the whole parts. The whole part. So we're going to put 0 point. Now 7 hundredths, we know the hundredth is the second spot, so we know we're going to go here. But we only have one number, so that's not the hundredths. This is the hundredths, and we've given a number, so we know the number goes in that spot. But what goes here? Well, because there's no number given, then we assume that it has a 0 there. A 0 always fills any place value that you're not given. So 0.07 is the same thing as 7 hundredths. Because the position of the digits in a number, the position matters because our system is a positional system. We need to make sure we take that into consideration when we add or subtract or do really any kind of arithmetic on decimal numbers. Addition and subtraction is probably the easiest to do because what we really need to do is make sure we're adding up like quantities. So 3.5 and 6.14, what's important here is to make sure we understand that 3.5 is the same thing as 3 ones and 5 tenths. 6.14 is going to be 6 ones, 1 tenth, and 4 hundredths. Now we wouldn't add 6 ones to 5 tenths because they're not the same quantities. 5 tenths is much smaller than 6 ones. However, 3 ones and 6 ones are the same quantity. So let's take 3 and add that to 6. Now 5 and 1 here, 5 tenths and 1 tenth, those are also the same quantity. So let's make sure we add those up. Now the 6.14, right, the 4 there is 4 hundredths. The first number does not have anything written there. So we could write a 0 if we want there. We can write zeros for any place that we don't have. So it's 0 hundredths and 4 hundredths. So I'll write that out just so we can see it. And what you'll notice here is I've written this in a special way so that the like quantities are lined up, and we can just go straight down for addition. What you also notice is that because I did this way, these decimal points are also lined up. And in fact, that's kind of the trick to doing this by hand, is if you line up the decimal points, all of the place values will line up as you want. And we can add this number like we do any kind of number, going straight down. So 0 plus 4 is 4, 5 plus 1 is 6, drop the decimal point down, and 3 plus 6 is 9. So 3.5 plus 6.14 is 9.64. All right, let's look at another one. 9.242 plus 0.87. So we can read off the first number as 9 and 242. Sorry, I shouldn't say and. 9 and 242 thousandths, because this last 2 is in the thousandths slot. The 0.87 is 87 hundredths. There's no and in there because the decimal point, there's no whole number. Using the same thing we did in the previous problem, 9.242, all we have to do is line up the decimal point. And if we're missing a place value like we are on the bottom here, we can just add a 0. That won't change the number at all. 2 plus 0 is 0. 4 plus 7 is 11, so you drop the 1 and carry the 1. 1 plus 2 plus 8 is 11. 1 plus 9 is 10. I'm going to drop the decimal point, just to make sure we don't forget that. 1 plus 9 is 10, so drop down the 0, add the 1, and then of course just goes straight down. So 9.242, or 9 and 242 thousandths, plus 87 hundredths is 10 and 112 thousandths. All right, here are 3 more problems. For the first one, I'm going to, for the 8, that doesn't have a decimal point, so I'm just going to add it in there. And I'll write a 0 next to it, just to kind of keep the continuity of how we write numbers. And then I'm just going to write them all vertically. So 2.1, 8.0, and 0.593. And we are adding all of them, so we can do this quite easily. I'm going to add in the zeros for the place values that are missing, and go straight down. 0 plus 0 plus 3 is 3. 0 plus 0 plus 9 is 9. 1 plus 0 plus 5 is 6. Bring the decimal point down. 2 plus 8 is 0. There's the 1 up there, and then bring that down. So 2.1 plus 8 plus 0.593 is 10.693. Next one, subtraction works the same way as addition. Make sure you line up the decimal points and subtract. 6 minus 1 is 5. 6 minus 4 is 2. Bring the decimal point down. 2 minus 3, we can't do that, so we have to do, well, it becomes 12 again. 12 minus 3 is 9, though. So we get 9.25. Continuing, 28 is 28.0. So I'm going to write 28.0 minus 15.59. Add the 0 place value, and you see that we need to do some carrying over some digits. So make this a 7, this becomes a 10, make that a 9, and that becomes a 10. And if you didn't know why we added 10, that's because each place value one above the other is 10 times as big. So the 8 was 10 times the 0. So when we changed the 8 to a 7, we gave this one an extra 10 value. And that's because our number system is base 10. Okay, 10 minus 9 is 1. 9 minus 5 is 4. 7 minus 5 is 2. And 2 minus 1 is 1. So there are the answers for those 3 problems. Now let's do some application problems. Here's a pipe, and the blue part in the center there, that's the interior. So we're kind of looking for what's the diameter of the interior of this pipe when these sides here are kind of like the wall thickness of the pipe. If the wall thickness of each pipe is 0.0025. Now what would that be as, saying it in English? That'd be, so, let me write it a little bit bigger here. 0.0025. This is the tenths, hundredths, thousandths, 10,000ths. So this would be 25 10,000ths. A little weird just to say it in English, but it is what it is. So to find this interior diameter, all we really need to do is take off each of these values from the total diameter of the pipe that we're looking at. So we can just take off, so it's pretty much like this. 3.3750 minus 0.0025, and then minus again 0.0025. Now you can't really do this in an up-down method all at once. We have to do this in parts. That's because we're doing 2 separate subtractions, and it doesn't really work out really well. You can do addition, all in one go, but not subtraction. That's fine though. We can just do each one separately. So this is the first. This is just going to be this portion here. 5. Do the subtraction. That's going to be 4. 10 minus 5 is 5. 4 minus 2 is 2, and we get 73.3. Then we subtract again. We get 0.073.3. And there is our final, like the interior diameter width of the pipe. This will of course be in inches. The double apostrophes, that stands for inches. So we have laminated glass that has 2 outer layers. Let's make a note of here. 2 outer layers that are 2.60 millimeters thick, and an inner layer, a single inner layer, that is 0.38 millimeters thick. What is the total thickness of this type of glass? So we have an outer layer, we have 2 outer layers. Let me do it like this. 2 outer layers that are 2.6. Let me draw a little bit better here. And then an inner layer. It's like that. So this is going to be 2.60 millimeters. This here is 2.60 millimeters. And the inside is 0.38 millimeters. So it's asking us, what is the total thickness of this type of glass? So what is this distance here? Well, hopefully you see it. All we have to do is add up all of these thicknesses. So I'm going to write them vertically here, and make sure you line up the decimal points. If you do that, then the addition is pretty straightforward. 0 plus 0 plus 8 is 8. 6 plus 6 is 12. Plus 3 is 15. So the 5 goes down, the 1 goes up. Bring the decimal point down. 1 plus 2 plus 2 plus 0. That's 5. And these are all in millimeters, so the answer is going to be in millimeters as well.